So I want to talk today about hybridization. And in hybridization, we take our atomic orbitals, and if we focus just on the valence orbitals that most atoms have, we're talking about an s orbital and 3 different p orbitals, and we mix them together. So when atoms make bonds with other atoms, they mix or hybridize their orbitals, and they use these hybrid orbitals to make bonds with other atoms. The atomic orbitals aren't used, the hybrid orbitals are not used. And we can mix together some of these orbitals, like all 4 of these, or we can mix together some of them. So let's look at what happens under these different circumstances. And first, I want to look at the situation where we mix all 4 of these. So we're going to mix together an s and a p and a p and a p. We're mixing together an s and 3 p orbitals, and we call this sp3, an s and 3 p's. And we get 4 of them, and I'm going to show what they all 4 look like together when we see them in conjunction with one another. It looks like this, with one going straight up and one going away from me and 2 coming out towards me. And if we sort of look at this sort of easier to visualize representation, it looks like this, with one orbital going straight up. These thicker lines mean they're coming out towards me. So the regular line is in the plane of the paper. The wedged one is coming out towards me, so 1 coming out towards me, 2 coming out towards me, and the dashed one means it's going away from me, so 1 is going away from me. The bond angle in a sp3 hybridized atom is 109.5, so all of these bond angles are 109.5. We call this shape tetrahedral. So let's look at some example of atoms that are tetrahedrally hybridized when they are forming their bonds. First, I want to start with CH4. And the Lewis structure is this, carbon with 4 hydrogens around it. Really important to remember, an atom that has 4 different groups around it, whether it be atoms or lone pairs, if it has 4 different groups around it, it's going to be tetrahedral in shape, and it's going to be sp3 hybridized. So let's look at sort of the 3-dimensional picture of CH4. And it looks like this, with 1 hydrogen coming out towards me, another hydrogen coming out towards me, 1 hydrogen going away, 1 going straight up and down, and a bond angle of 109.5. I want to look at a second example of the sp3 hybridized molecules, and for that we're going to look at water. And you might say, wait a minute, the oxygen in water only has 2 hydrogens around it. It's not tetrahedral, because tetrahedral has to have 4 things around it. Very important, always look at the Lewis structure first. So the Lewis structure looks like this, and you can see I have 2 lone pairs on the oxygen. The 2 lone pairs and 2 hydrogens make a total of 4 things. So water is going to be tetrahedral in geometry. So let's look at the geometry. And you can see it's tetrahedral. 2 hydrogens, 2 lone pairs. Let's next look at the case where we don't use all of the orbitals. Let's look at a case where we use the s in 2 of the 3 p orbitals. So we're going to look at mixing an s and 2 p's. The third p is still there. We're just not adding it in with our s and the other p, but it's still there, and we're going to use it in a few minutes. We call this type of orbital sp2. And if we look at the shape of the sp2 orbitals when they're arranged with one another, we have 3 of them, and they look like this. They're all in the same plane, and they're sort of triangularly located, one pointing at the corner, each pointing at the corner of a triangle. We call this shape Trigonal Planar because, like I said, each bond points at the corner of a triangle, and it's planar, it's completely flat. All the atoms are in the same plane. The bond angle in Trigonal Planar is 120 degrees. Let's look at some examples of Trigonal Planar molecules. So I want to start with CO3 minus 2. And just like we did with the tetrahedral, the first thing we need to do is we need to make sure we draw the Lewis structure. So here's the Lewis structure. So you notice that there are 3 different things off of the carbon, the oxygens, 3 oxygens, and they are in a trigonal planar orientation. So let's look at the trigonal planar shape of this molecule, and I'm going to draw it slightly differently so that I can emphasize a few different things. So I've drawn it so 1 carbon-oxygen bond is in the plane of my screen, 1 is going back away from me, 1 is coming out towards me. All 4 atoms are in the same plane. Trigonal planar, 120 degree bond angle. Now, you might say, okay, that's good, but one of the oxygens has another bond on it. It has a double bond here, and that's true. And where does that double bond come from? Well, remember the p orbital that we said we have left over? Well, the carbon has one of those p orbitals, and the oxygen has one of those p orbitals. And those are used to make another bond. So let's try to look at that. It looks like this. So this is my carbon, and the p orbital that I had left over is right here. This is my oxygen, and the p orbital that I have left over is right here. And they overlap side by side. So this double bond is made up of two different kinds of bonds. It's made up of one bond involving the hybridized orbitals, and it's made up with the second bond coming from the normal p orbitals. We have names for these two different types of orbitals. These different types of bonds. One of the bonds comes from the hybridized orbitals, one comes from the p orbitals. So we have names for these two different types of bonds. The bonds from the hybrid orbitals are called sigma bonds, and they're given the Greek symbol sigma. The ones from the regular p orbitals are called pi bonds, and they're given the symbol pi. So in this molecule of carbonate, I have 1, 2, 3 sigma bonds and 1 pi bond. A double bond is made from 1 sigma and 1 pi bond. So let's look next at the case where we only add the s in one of the p orbitals. So let's look at that now. So this time we have an s orbital and a p orbital. When we add them together, we have an sp orbital. We got two of them, one pointing this way, one pointing that way. We have two. Since we didn't use these p orbitals, they are still left. We still have them. The general shape is like this. It's linear. It's in a straight line. The bond angle is 180 degrees. So I want to look at some examples of this, and the one that I want to start with is acetylene. The formula for acetylene is C2H2. And always we start with the Lewis structure. This is the Lewis structure. You can see it has a triple bond between those carbons. If we think about the sp2 having 3 things around it and the sp3 having 4 things around it, an atom like this carbon right here that is sp hybridized has 2 things around it, a hydrogen and the carbon. All 3 of the triple bonds count as one thing. We're only looking at the carbon. So 1 carbon and 1 hydrogen. 2 things around it, sp hybridized. So I want to look at the sp bonds. There are, these are, like I said, these are hybrid orbitals, and so this is sort of the depiction of those sp bonds, orbitals making sigma bonds. Remember, we said that if something is using a hybrid orbital to make a bond, it is a sigma bond. So this is a sigma bond, this is a sigma bond, this is a sigma bond. Now I want to talk about those other 2 bonds that are making up part of the triple bond. We've got 2 more bonds, and just like before when we had leftover p orbitals in carbonate, we have leftover p orbitals for our acetylene too. In this case, each carbon atom has 2 p orbitals left over. One is going straight up and down, one is going out and going back. So this carbon has one going up and one going out and back. The other one also has one going up and down and out and back. And those 2 p orbitals on each carbon make 2 pi bonds. One here and one here. So a triple bond is made from 1 sigma and 2 pi bonds. Now if we try to put things together and look a little bit more at what's going on with our sigma bonds and our pi bonds, we can do that. So I have this carbon right here with its sp orbitals like this, and then other carbon is right next to it with its sp orbitals, and they overlap to form the sigma bond. So this overlap right here between the 2 sp bonds is my sigma bond. Now my hydrogens are there too, but the thing about hydrogens, they're in the top row on the periodic table, the n equals 1 shell. In n equals 1 shell, you cannot have any p orbitals. You don't have any 1 p orbitals. So the only orbitals hydrogens have are s orbitals. The hydrogens are not hybridized. They use s orbitals for making their bonds. So here are my 3 sigma bonds. Now I can put my pi bonds on there as well. I can try it. It's going to get really messy and confusing, but we can try to do that. This carbon is going to have a p orbital, and this carbon is going to have a p orbital. So let me put those in first. I'll draw 1 pi bond first. So p orbital here, p orbital here. Here's one of my pi bonds, and I'll try to draw the other one now. I'm going to have pi orbital going back on this carbon, and a p orbital going back on this carbon, and p orbital going back on the other carbon. So let me draw that. And here is my second pi bond. P orbital on this carbon overlapping with a p orbital on this carbon. So my triple bond is 1 sigma bond and 2 pi bonds. 1, 2.